All right, so thanks for the invitation. Well, I'm a local, but this is definitely my first time visiting this hall at Hong Kong U. Okay, so the talk I'm going to give today, well, the title looks a little bit fancy, but then it actually two parts. One, it's a level set-based variational principal flow method. So it's a numerical approach. So we are trying to use computer for the problem. And the problem is dimension reduction on Riemannian manifold. So now, even though we use this really fancy word, but then all we actually try to do is just to try to explain data on surfaces. Okay, so but definitely the approach can be generalized to higher dimension. By higher, it doesn't really mean like 100 dimensions or not even 10. We are trying to work on 4-dimensional data. The issue here is just it's because of the numerical approach we try to present here. It's a PD-based approach. It's a variational approach, and that's why we are not really able to try to do things in really high dimensions like 100. This is a joint work with several people. Okay, so. My former PhD student, Liu Hao, well, I'm sorry for this, the fonts mismatch because I was using Mac, and then, you know, there's compatibility issues between Mac and Windows here. But my former PhD student, Liu Hao, so he's currently doing his postdoc at Georgia Tech. On data, so he's really trying to use machine learning type things to do things. And then our collaborator, Jigang Yao from National University of Singapore, our former president, Tony Chan, and he just moved to KAUST. My former master's student, Tony Wong, he's currently doing his PhD at UBC. We are using a work developed with Tony Wong on trying to compute and extract the geodesic distance on surfaces. This is our campus. If you have never been there, so feel free to come visit us. We're happy to host your visit. Okay, so here's how I have to talk, 4 parts. I will first give a very brief introduction to the background, so the problem we are trying to solve. I will briefly talk about the numerical approach, the representations of the manifolds, and our goal in the first part. And then I will talk about our proposed method in the second part. I will, if I have time, then I will talk about some implementation details. In the third part, then I will show you some numerical examples. Okay, so I'm sure there are some people doing statistics in the audience. So this is a very simple problem to solve. So I give you some data, and then what I want to do here is to try to estimate and look at the variation of this data set. Okay, different numerical approach. One, well, really simple is the linear regression. Okay, so that's kind of undergraduate level materials. Then a slightly more fancy one would be the PCA, Principal Component Analysis. Okay, so and then if you really want, then you can actually do a curve fitting. Okay, so if you want some high order explanations of the data set. But then there are problems about all these different approaches. For example, if you're looking at curve fitting, you need to have an estimate of the data in some sense. You need to provide some basis. Okay, so say if you're using this type of things, this example I'm showing here, then you really need, say, a polynomial basis, things like that. So you need to provide some parameterizations of the data. Now, what we want to do here is the following. I will give you some data, so there are those black dots. They satisfy some constraint. Okay, so the constraint would be this nonlinear constraint. In this particular figure, we're showing that the data would be on the sphere. Okay, so on the sphere. And then what we want to do is to, for example, one is to extend the PCA idea to the data set on this surface. Okay, so and what we want to get is the blue curve or the or the red curve on the surface, okay? And we use that to explain all this data. And clearly, those data would get noise, but then, essentially, they're still staying on the surface. Now, at the same time, we want to obtain some curve, and they are not parameterized by the polynomial basis, for example. We try to get this curve to explain the data. Okay, so that's the ultimate goal. But clearly, the idea can be extended to other surfaces. A little bit later, I will show you some examples, including, but then it's still two-dimensional surfaces in 3D. So we got a torus, for example, and then the data, okay, you see here, might not form a closed curve, but for example, it can be open curve on the surface, or you might get more than one curve on the surface. So in those cases, then what you can do to try to get those curves at the same time would be a little bit challenging. Now, clearly, there are different approaches for extending PCA to surfaces. For example, one way is the so-called PGA approach, principal geodesic analysis. What you want to do is to extend the geodesic distance extend the Euclidean distance to geodesic distance. Okay, then you have to be able to compute the geodesic distance between the points to any 2 points on the manifold. So the computation could be a little bit tedious and tricky. Another approach is the so-called tangent space PCA. What you want to do is to, from the data, so you will project the data onto the tangent plane, okay, and then you will do the standard PCA on the tangent plane. Okay, so now in the high dimension, then all the computation will still be in the standard Euclidean space. Okay, then you can just use the standard PCA approach to compute that. More recently, our collaborator, Jigang, so with his collaborator, so they developed this so-called principal flow approach. Now, here's the idea. Now, we have manifold, so that's a blue surface there. The very first step is to try to first estimate the mean of the data. Okay, so you compute the Frechet mean. Okay, so that's the, for example, the green dot here. Then you do something really similar to the tangent space PCA. Then this is the tangent plane. Okay, then you use the log map. Okay, so to project the data point onto the tangent plane. So you got those blue dots. In this Euclidean space, then you would do the standard PCA. So you got that principal component. So that's the green vector. Now, that particular green vector will tell you the direction, the tangent line of the curve you're trying to estimate, you're trying to determine. Okay, so you match a little bit in that green direction, and then you project yourself back to the manifold, to the surface. Okay, so then you got a little bit segments on the interface. Then you repeat this whole process over again. So it start at that point, you compute the tangent plane. So this is the red plane here is a new tangent plane. And then you compute the tangent plane PCA. Then you match a little bit further. Okay, so that's what we are seeing right here. Then you match a little bit on that direction, and then after that, then you match backward. So then eventually, this is the curve you will get. Okay, so that's the black curve. Now, the black curve is obtained by using a really small step size. Okay, then you get well, it looks like a smooth curve. If you use a large step size, then you will get this red curve there. Okay, so there are things you have to tune in this particular approach. One is the step size. Two, well, that's a little bit more crucial, and that's, well, starting from the Frechet mean probably is not a good explanation to the data. And this is one example. Now we still got a sphere over there, and then we got some data points, the dots there. And then if you start all your computation from this green dot, the Frechet mean, then it doesn't really matter how you pick the step size. You will not be able to get a curve explaining the data well. Okay, so that's a problem. Second issue about this approach is that not only about the initial condition, the initial point, but then if the data look like this, so we still get a sphere, but then we get a data, well, this kind of a segment from each other, it's pretty much impossible to get both curves at the same time. Well, if you are able to kind of separate the data into two groups, say if you're only looking at that group, even if you get away from the Frechet mean, say even if you pick a point here, then you might be able to trace this blue curve here on the bottom. But then, well, because you always start your computation at one point, then you will just be able to get this. And then after that, well, probably there's another group, then you compute this the other blue curve. So that computationally, that's a bit troublesome, at least to us. Now, this is what we call the Lagrangian formulation, meaning that, well, you have the curve parametrized explicitly. So you have a curve, okay, you call it gamma, parametrized by a certain parameter t. So you match a little bit, so that's 1 delta t, and then 2 delta t, and then you get the whole curve. So that's what we call the Lagrangian representation. Our contribution is the following. We propose a fully Eulerian formulation. Okay, so Eulerian formulation means all the computations will be done on a fixed mesh. Okay, so we will not have point tracing the curve. We will not have point evolving in time. But instead, all the computation will be done on a fixed mesh. Okay, so there are two things, two implicit representations. One would be the surface itself. Okay, so the manifold, the yellow surface, we will introduce an implicit representation for that. And then two, the curve itself here, we will not have an explicit parametrization, but then instead the curve will be represented implicitly by another function. I'll come to that in just a second. The method should be robust to noise. So as you can see here, there are lots of noise in the data, and then we will still be able to get a nice curve to try to explain the data. We also, in our approach, there is also a parameter to balance the contribution directly from the data and also from the principal flow. Okay, so we will take the idea of the principal flow and then we try to add it into our Eulerian representation. Now we got lots of experience doing computations on surfaces. On the top, so this is the evolutions of a surface, a dumbbell shaped in motion by mean curvature. Okay, so the challenge is at this point, so the surface will split into two. And then if you're using a Lagrangian representation, meaning that you put points on the surface and then if you evolve it, then at some point you have to cut the connectivity of the triangles and then reconnect them. So the Eulerian representations we have been working on for years can be able to handle that topological change naturally. So we are from the level set community, so we have long experience working on that. And then there are other numerical approaches also that we classify them as implicit representation. The closest point method by Collins and Steve Roofs, and they also have other numerical approach. They are also able to compute solve equations on surfaces. Okay, and then with my former PhD students, we are also developing other numerical approach to represent the surface. And what we try to do here is to solve reaction diffusion equations on surfaces. We computed the eigenvalues of the Laplace spectromy on surfaces, and that's for example, we can use that for surface classifications, dimension reductions, and etc. We also add in motion to the representation. What we're trying to simulate here will be the turning patterns on the surface, and at the same time that will contribute to the evolutions of the surface. This is a slide very briefly summarize different Eulerian representation, but I don't think I got time to go over it. We are, in this particular work, we are using level set representation. So meaning that we will introduce a function phi on the mesh so that is equals to the distance away from the surface. So, if you're not familiar with the level set method, so this is what we try to do. So we're representing a circle using this particular function, and then the circle will just be certain level set of that. Okay, so this is the level set method. But anyway, so that's not the main point of this this work. Now this is our proposal. Now what we try to do here is to determine a curve. We call it gamma. Okay, so gamma is the unknown we try to determine to minimize this functional. Now there are two terms of this energy. The first term is the d function. Now this d function is a geodesic distance from the point x on the curve, okay, so on gamma, away from the data set. Okay, so if there's no noise in the data, and then if you got many points on this curve, then the distance, well, you try to determine it will be 0 from this term. So you try to determine a curve gamma will stay along with the data, and so it will be 0. Okay, but then clearly it won't be 0 if there are noise in the data. The second term, we try to take some information from the principal flow, and P there would just be the principal direction. So that's from the tangent plane PCA. Now n here, okay, so we try to minimize this term. That means we try to have an n perpendicular to this direction P. Okay, so n will be the normal of the curve on the manifold. And then this P would be the estimate from the principal flow. We try to determine the curve. One, try to explain the data. Okay, try to align with all the data. And second, at the same time, we try to take some information from the principal direction. Okay, so this is the thing we try to minimize. Now the gamma here, if you try to solve this variational problem directly, it will be a Lagrangian formulation, because you are now parametrizing the curve gamma by the parameter s there. Okay, so you got some points on the curve, and then try to involve that. Now this is what people really try to do it in say image processing community. So those are the stick models try to do an image segmentation. So they really evolve the curve, try to minimize certain functionals and energy. But then we are proposing the following. We are trying to use a level set representation. So we have this Eulerian formulation. We introduce two level set functions. One would be for the manifold, for the yellow surface. Okay, so in this particular example, the yellow surface will be represented implicitly by this psi. And then we also have the blue surface. It's supposed to be a surface from here, but then we are only plotting the intersections of those two surfaces. Okay, so then we will have this blue curve on the surface, and this will be the initial condition. Well, in this particular example, this will be the initial condition for the gradient descent for this particular energy. Now we have to convert this energy in terms of the level set function. So we have to replace this gamma by some function, by the function psi and phi. It's kind of standard in the level set community. And the second line is what we did. Well, it's straightforward by just replacing this integral. So this integral will be on the curve, but this particular integral will be in the whole space R3. Okay, so since we have an underlying mesh, which is Cartesian in space, so this particular integral can be done easily. Okay, and then to take the information from the curve, then we have two delta functions. One would be to the surface, and one would be to the zero level set of the blue surface we got on the previous page. Similarly, we also have those terms in these two terms in the second guy, okay? And then what's next would just be the standard calculus of variation. So we try to minimize this function with respect to those two functions, phi and psi, okay? My poor student did all these computations. But anyway, so eventually this is a PDE you have to solve. Now, since the surface is fixed, so we do not solve a PDE for that. The manifold, the yellow surface is fixed. What's evolving is the blue surface. Okay, so this is the equation governing that evolution. There are two terms in this PDE. One is the diffusion term, so this is a diffusion term. And if you have some experience on things like geodesic active contour in image processing, this diffusion terms will drive the evolution of the curve so that it will strain and that eventually it will stay on the surface. Okay, so that's the diffusion term, so the standard elliptic PDE. The second term looks a bit weird. So we have certain vector here. So this looks like an advection term. Now, what's important here is that, one, it doesn't matter about the psi of P. So from the PCA on the tangent plane, well, you don't have the psi. So it can be pointing this way or that way. And then in this term, it doesn't really matter whether you got P or minus P from your computation. So it will give you the same quantity. Oops. The second one is what it says is that the magnitude of this guy is bigger than 1. So you always have contribution from the second term unless the gradient of your level set function is perpendicular to the principal direction. Now, the gradient of the level set function is parallel to the normal of the surface. Okay, so because the normal is just grad phi divided by its norm. So this guy will be parallel to this n. So you will always have contribution from the second term unless, okay, so meaning that you actually reach the thing where it should stay. Unless the normal of the level set function is perpendicular to the principal direction. Okay, so it seems okay, right? So it matches with our intuition. So this is a PD we need to solve, and then, well, there are lots of standard packages for this. Well, because this is a linear equation, and then you can just use, say, if you are from the numerical PDE field, then you can just use the standard TVD RK, we know, and etc. to solve this equation. Okay. So now there are several issues about the implementation we might need to spend some time on. One is this particular D. Okay, so remember what is D. Now D would be the geodesic distance from the given data point to elsewhere. Okay, so this is something we have to compute. Second is that, well, computing the principal direction P at each grid point, well, at least those are near the manifold, the yellow surface. Well, it's kind of time consuming, but then you can treat that as a pre-processing step. At each grid point, then you compute the local PCA, and then you just solve this PDE. And then the third thing is the level set regularization. So you solve the PDE, but then there are always errors, and then the level set might be kind of flat, and then extracting back the zero level set from that might be challenging, and etc. But then from the level set point of view, then they are rather standard issues, and then there are ways to solve it. I might not have times to go through all these details, but let me just very briefly talk about our approaches to solve this problem. One, the first problem, so I might just have time to talk about the first problem, is to compute the geodesic distance from the data point. Now, what we are showing here is a very first attempt, so that's from 2001. What people propose to do is that, well, if you try to compute the geodesic distance on the manifold, then what you can do is you, well, extend the surface to a computational tube, and then you just do the computations within the tube. Okay, so that's rather straightforward. But then it turns out this particular approach will not converge. And that's why later we propose a way to modify this by incorporating an extra boundary conditions. Then we have a converging method. Now, well, there are lots of fake curves here, so probably let me just skip that. I'm sorry about that. If you're interested in all this, we can talk a little bit later. Maybe I just showed you some numerical examples. Now, so these two are some really simple examples. So we are given data on a sphere or a data on a torus. So we got those black dots there. And then those black dots are generated by first, so you assume you got the so-called exact solution. So that's the red curves on these figures. And then you pick some random points on this red curve. And then further, you add some noise to it, okay? And make sure that, and then after that, you project it back to the surface, okay? So that's how we generate those black dots. On the left, so they are the initial condition we pick for our computation. We remember the gradient descent, the PDE. So we just solve the PDE on the underlying Cartesian mesh. And then what we got would be the blue curve on the right. Okay, so that looks perfect. Now, but then these two are some really simple examples. Now, this is a more challenging example where the data are generated from two separated circles. So we got two classes of data on this manifold. But then the initial condition, once again, the blue curve, we have no assumption at all on how the distributions of the data are. We just have this blue curve initially, make sure that it surrounds all the data, okay? And then just solve the PDE. Now the PDE, the curve, the zero level set of the PDE on the surface will evolve in time. And then it will automatically reconnect itself, because in the evolution, we actually don't care about the connectivity of the data. So it's the solution of the PDE tells us, well, that's probably there's two groups. There are more than one groups in the solutions. And then it will automatically do this topological change. And then this is what we get. We can also do open curves. So the data would be this particular open curve on the yellow surface. And then this blue curve is our initial condition. And then this is the solution we obtained. Okay. Now, the method is also can handle outliers. So as you can see, there is groups of data kind of away from this group. And then our method can naturally, so we didn't do anything, but the curve will just evolve itself and then get past those data. Remember, there's a parameter lambda in the model. So it's actually tuned, give the user a way to tune the contribution from the geodesic distance term, and also how much you trust the information from the principal direction. Okay, so lambda equal to 0 means you just get rid of that term. Okay, so you just try to match the data by evolving the zero level set, the curve, so that it best match with the data. Okay, so that's what we got. So there are missing things. Well, we try to get something like a square. So there are supposed to be corners at the curve, but then because of the smoothing, so we get rid of that. Now, if you trust the principal direction a bit more, so you can see that the curve will go in that principal direction, in that geodesic direction a little bit more. Okay, so so it looks like a little bit more than a square. Now, this is the last example we tried, and once again, it's just a two-dimensional surface in R3. Okay, and then it turns out to be also a sphere. Okay, now what we try to do here is to try to reconstruct the tectonic plate from the earthquake epicenter. So we just pull out some data from the earthquake data, and then we try to reconstruct a curve from it. And this is another example. Okay, so we construct, and then we try to reconstruct that part of the tectonic plate. Okay, but once again, like what I mentioned earlier, This is a very simple model with many limitations. One is the computational efficiency. Now, in this work, we are solving some PDE in three-dimensional space. Remember, so we got the surface, the two-dimensional surface embedded in three-dimensional space. So the computational mesh will be in 3D. So it's slow. For all those examples we did, so probably it would take around an hour to get the solution. A more challenging issue about this approach is about the dimensionality. Like what I said at the beginning, we are trying to work for things in 4 dimensions, but that's already required some careful implementations of the level set method. There is a local versions of the level set method. You might be able to solve the PDE in a small neighborhood of the manifolds, but then you still need a careful implementation of the algorithm. But eventually, what we try to do is actually, at the same time, try to learn the underlying manifold, the yellow surface at the same time. So, so that's why we try to develop at this point an Eulerian, an implicit representation of that, because at the same time, we can also evolve the other level set method. Okay, so there are 2 level set functions we can evolve in time, and that all can be applied to a manifold learning. Okay, so I guess I will just stop here. There are 2 references for this presentation. One is with Tony Wong, so how to solve the Iconic equation on an implicit surface, and we use that to compute the geodesic distance on the surface, and this is the main reference for this presentation. Any questions, I'm happy to take.
Very nice talk. It looks like your problem is very similar to the shape optimization or topological optimization. Is there any connections?
Yes. Yes. In fact, if you just have the first term in our proposed model, it looks really similar to another work in the level set community. Well, and I took that page away. And that's, well, the application is the following. So it's for reconstructing a surface from point cloud. So imagine, you just have points in this 3-dimensional space, and then you try to obtain an implicit representation of that surface. And then you can just look at the first term, and then you have the zero level set, and then evolve, and then it will stick on the unknown surface. So that's for the shape reconstruction. And that's the difference here is that we are extending that Euclidean computation to things on manifold, on surfaces. Okay, so it's similar to that.
But you don't actually solve an optimization problem, right? Because your optimality condition is the equation.
Yeah. So
you just solve it numerically.
Right. So we just use gradient descent. So we're not really tackling this functional directly, but then we have the optimality condition. We solve the Euler-Lagrange equation using gradient descent. So that's probably another reason why the approach is slow.
Yeah, so by that you can, if you can do gradient descent, you can much faster.
Mm-hmm. Yeah. Yeah, there are definitely other approaches for that. So especially the optimization community. So there are different, say, ADMM approach to handle this type of thing.